Good morning, good afternoon, and good evening, ladies and gentlemen. It's my pleasure to welcome you to ECT Store Heavy Flavor Transport Workshop. Also on behalf of my fellow organizers, Ralf Averbeck, Xin Dong, Paul Gossot, and Xingyang Wang. Now, as you all know, we're running this meeting basically 14 months late. And we still have to go in the online format, which is a bit unfortunate, but we thought that further delay would be maybe even more detrimental to our course. So in that sense, we are particularly grateful that you still decided to join, although the circumstances are maybe not as great as they would be if you would have our meeting in the unique environment of the ECT store. But still, we hope that we'll have fruitful exchanges, and in the spirit of some similar initiatives over the past 2 or 3 years, we hope that we can make further progress on understanding the theory and phenomenology of heavy flavor transport, and in particular, how we can catch up on understanding the beautiful data that we have and still be getting from RIC and LHC. So in that sense, again, welcome, and I hand it over to Ralf for a few more remarks. Ralf Averbeck.
Yeah, thank you, Ralf. Actually, I have only one brief remark to add, and that is I would like to advertise the support that we have from Strong 2020, which is a program within the European Union's Union Horizon 2020 program. Of course, we have been much more grateful to use this support last year to support all our travel, but still, this is very much appreciated. And what the speakers are asked to do is to for example, acknowledge the support of Strong 2020 in case of any publications coming out of this workshop. And it would also be nice to feature the Strong 2020 logo on your title slide. I will send an email to all participants with that logo, such that it should be very easy to accommodate that request. And that was essentially all I wanted to add. Maybe one more thing. There will be a presentation later this afternoon by Giuseppe Bruno, who together with Jörg Eichelin is coordinating this Strong 2020 initiative. And we will all learn more about Strong 2020 from Giuseppe this afternoon. And with that, I would hand over to Gerd Arz for a welcome address from ECT Star. Please, Gerd.
Thank you. So I'll also share some slides. Can you see the slides?
Yes.
Okay, so on my behalf as ECT Star Director, I want to welcome all of you. And indeed, I'm very happy that you are organizing the workshop and joining the workshop in this online environment. It's very important, of course, for ECT Star to keep going and to keep developing activities. And similarly, it's very important for the community to keep going and not simply wait for the pandemic to pass. I mean, it's been over 1 year, so hopefully the end is in sight. But as we know from the past year, you cannot be too sure about when it's happening. Now, many of you have been at ECT Star many times, but for those of you who haven't, I just want to say a very few number of things. So ECT Star was established in 1993, so a few years ago we had the 25th anniversary, and we're a member of the expert committee of NUPEC, Nuclear Physics European Collaboration Committee. And what's very important is that it's a community-driven bottom-up center. And so we're always looking for input from researchers to contribute. And the activities we do, of course, as you know, is research in theoretical nuclear physics, activities between theory and experiment, and also related areas of research. And I'll say a few things about that later. And finally, the training of young researchers. And that's both explicit training in the training programs, but also the participation in the workshops like these, where it's important for everyone to contribute, both with knowledge and also with questions, of course. So here's an overview of the activities of 2020. It's a little bit small, but the poster is also on the website. All activities are now online till August, and very soon we will decide on what happens afterwards. The decision is not in the hands of ECT Star, but it's decided by FBK, the local funding agency, to see what happens. And of course, we'll tell you, as soon as we know how the program will continue, what it will look like. There are two important training programs which I'd like to bring to your attention, because you may want to send a student to these. Both of these will be online, but we have experience now. The talent school ran last year online as well, and actually many students joined. Over 150 students joined, and so it's in fact easier to join because you don't have to travel and so on. So the talent school this year will be on machine learning applied to nuclear physics, experiment and theory. And the doctoral training program is on high energy and nuclear physics within quantum technologies. And in the DTP, the interesting thing is that half of the lectures come from kind of the high energy lattice field theory community, and the other half come from the quantum technology community. So it's really bringing these two groups together. And so it's an excellent opportunity to learn, both fields. So all the fields you're not familiar with. So if you recommend your students, that would be great. There's also a visitor program, which has been obviously dormant in the past year, but once we get back going, please contact the center if you want to spend some time there, even if there's no workshop happening. We just started a Twitter account. As you can see on the top here, the 4 tweets have been sent, so it's all very new. But please follow the center. And in the same way, if you want to tweet during the workshop, personally, I'm not a tweeter really, so I'm not an expert. But if you are, you probably know how to hashtag and follow and all of these things. So, so please do so. A little bit about the related areas. So from its beginning, the ECT Star has been very broad and covering workshops related, say, to cold atoms, condensed matter physics, many body physics, etc., etc. And in recent years, there's an interest both locally in Trento, but also, of course, internationally in quantum technology and in machine learning. And as we know, all these items are somewhat related to nuclear physics. Say, machine learning proposals to look at the quantum many-body problem, or other strongly coupled systems. And so I just want to advertise here to keep, to be very open-minded and see what opportunities there are for nuclear physics to look at these new directions that are available, because they're quite excited, and they're also very well funded, just as a strategic remark. The scientific board currently consists of these people here. Marcella Grasso is the chair. This is one example of an activity that is community driven, because membership of the board is suggested by the ECT Star Associates. And all people who join in workshops become an associate for a certain amount of time, and then it can be renewed. And so these board members are serving a 3 years term, and there's every year there's a turnover of one or two people. A few words about funding. So local support comes from the Bruno Kessler Foundation. There's support from all the national funding agencies, which is very, very important. And then there is EU funding, Horizon 2020 funding. And what is interesting, I think, is that ECT Star is recognized as a transnational access facility by NUPEC, and it's the only theory center that is recognized like this. All the other ones are experimental labs. So that puts ECT Star in quite a special place, which we should treasure, both within the community, but also with respect to our funding agencies. Here's an overview of all those agencies. So the FBK, European funding, and funding agencies in the different countries, and some additional ones in Germany. It was already mentioned. Thanks a lot for this clear mentioning. So it's indeed a strong 2020 workshop. And I'm sure Ralph will circulate the text to include in publications in case work either was initiated, developed, or completed through the workshop. It's a little bit important because we have to report back to Strong 2020, which has to report back to the European Commission how much work was achieved. and they actually do automatic searches based on these acknowledgements and grants agreements and so on. In any case, this is all what I wanted to say. So here's another photo of the villa, which you cannot see in person now. But I would say enjoy the meeting, and I'm looking forward to the talks as well. Thank you.
Okay, thank you very much, Bert, for this very interesting introduction, in particular to those of you, of course, who haven't seen it before, all the opportunities that the ECT store offers other than the workshops that we are all familiar with. So at 7:29, I think we should get started now. We have a rather dense program today and the following days, and it's important to stay on time. So it's my pleasure now to hand over the chair to Johanna Stachel, who kindly agreed to do that for the first session this afternoon, morning, evening. Thank you, Johanna. Please go ahead.
Okay, so we start with perfect timing. This session has 2 talks, and the first one will be an experimental overview by Andrea Dainese. Andrea is the physics coordinator of the ALICE collaboration, and in that sense, well predestined to give this talk. So Andrea, please go ahead.
Thank you, Johanna, and thanks to organizers for the invitation to give this overview talk. It's my pleasure to be with you, although only virtually. And I look forward to meeting you in Trento or somewhere else soon. So for this overview, I have asked actually Cristina Terrevoli if I could use some of the nice slides that she showed at SQM 2019, and I also used some of the nice compilation plots by Jing Wang and Roberta Arnaldi shown at Quark Matter 2019 and our probes 2020. So, oops. Yes, so this is the outline of the presentation. Here I have a usual time evolution of our collisions. And as you all very well know, heavy flavor is one of those probes that are sensitive and thus can bring information on essentially all the stages of the collision. So starting from the production and the early time when there are very strong magnetic fields in non-central collisions, and then of course during the plasma phase when they undergo interactions, energy loss, they may reach close to thermalization, and finally they also probe the hadronization phase. So then in the second part of the talk, if I have time, I will also cover a bit the experimental outlook. We are like all collaborations in ALICE, we are preparing for the next 10 years. And of course, heavy flavor is one of those sectors that will benefit most from the upgrades. So starting from heavy core production, let me show a few recent results on heavy core production in PP collisions. So you see on the left prompt and non-prompt D mesons, starting from PT almost 0 from ALICE, and then on the right you see B mesons from LHCb and from CMS. So now we have measurements that are quite precise over a broad range of PT from essentially 0 to 100 GeV, and they are compared systematically with several implementations of PQCD approaches with different schemes, and the data are described within uncertainties. But maybe an observation that is relevant for this workshop is that the theory uncertainties are much larger than the data uncertainties, especially for charm, as you see here for the D mesons. And therefore, for AA models, it may be better to consider using the PP data uncertainties or a proxy for them for the PT shape variations and studying their influence. Now, Since recently, we have moved also well into the baryon sector, especially for charm. So you see here several ratios, namely the lambda C over D0 on the left and the xi C over D0 in the middle panel, and these ratios are very large. As you see, the red lines represent what one expects from fragmentation as it occurs in E plus E minus collisions and as it is implemented in the baseline versions of PITIA, and one sees charm baryons fractions relative to the mesons that are much larger than that. In particular, at low PT, the lambda C over D0 is of the order of 0.5 and the xi C over D0 of the order of 0.2. Now, two things. Of course, this is crucial measurements to understand how hadronization occurs for heavy quarks, even in PP collisions, and then clearly in the heavy ion environment. And the other thing is the impact that this has on the estimate of the total charm cross-section. It is clear that with such fractions, one needs to account for baryons to have accurate measurements. So here I report a compilation that was in an Alice paper of 5 years ago. And essentially all the LHC measurements use only mesons. And so this will have clearly to be updated, and the cross sections will increase when also the baryons are included. Now, heavy quarks are also, of course, sensitive to initial state effects, and their P-LED, and in particular minimum bias P-LED, is a good environment to study these effects. We see that nuclear PDFs with shadowing describe the D meson are P-LED at 5 TeV. This is shown in Alice, and for LHCP, this is the RFB, so forward over backward PT distribution that don't need APP reference. For LHCb, we have also now the measurement at 8 TeV that maybe show a bit of tension with the 5 TeV at IPT, but of course uncertainties are large. At low PT, this is described by nuclear PDFs, and there are also in progress attempts to use this D meson data, in particular from LHCb, which are most precise, to reweight nuclear PDFs. And here you see the impact that it has on the gluon nuclear PDF, nuclear modification factor at 10 GeV, so it's essentially charm production at threshold, let's say the lowest PT, and the reduction of uncertainties would be very substantial. Of course, an important question is whether these measurements are completely free from final state effects, and the answer is not yet clear, obviously. So moving on, I said that charm quarks probe the magnetic fields at the early stage of heavy ion collision better than other partons, than other particle species, because they are produced early, so at the time in which the magnetic field is largest. So we have we expect to have two competing effects, a Faraday effect and a Hall effect, and we expect the V1 of the mesons to be sensitive, and in particular the difference between the V1 of D mesons and the V1 of anti-D mesons. So there we have a measurement by star that I show here on the left, and a measurement by Alice that I show on the right. So at the very right, the D meson delta V1 as a function of pseudo rapidity, and in the middle compared to charged particle. So what one sees is that there is a weak indication that the slope is different from 0 at the LHC, while at RIC it is consistent with 0. And of course, the measurements still have large uncertainty, but this is maybe related to the fact that the magnetic field is larger than the induced electric field. And clearly, data from the future runs, both at RIC and LHC, will be important to clarify this picture. Now, moving to the quark-gluon plasma phase, of course, we know that heavy quarks interact, they lose energy, and it is an important question to determine what is the relative role of elastic and inelastic processes, also as a function of PT. This will be discussed at length in this workshop, of course, and whether the expected flavor dependence of energy loss, in particular from color charge and from mass, is seen in the data and by comparing two models. So since quite recently, a couple of years, we have measurements for d mesons starting from PT equals 0. Here you see from Alice the invariant mass distribution of d mesons at close to 0 PT. As you see, the background is overwhelming and the statistical significance is still limited, but this is an important additional data point. And by looking at the RAA on the right, you also realize that this is an area now emphasized by the log scale where models differ quite largely. Because of course, the implementation, for example, of the radial flow shifts the spectrum to higher PT. So if you measure down to 0, you are sensitive to this depletion. And in addition, there is the effect of nuclear modifications of the PDFs. Now, it is also clear that in this region at low PT, it is already great to have first measurements, but the next generation trackers will play a crucial role to have a precise view. Now, this slide shows a nice summary of all the d meson RAA measurements at RIC and LHC. So from star here in green, where one sees a little bit more of a so-called flow bump at around 1 to 2 GeV in PT, and at LHC, ALICE, and CMS with nice consistency. And this flow bump seems to be less emphasized, which could be related to a less steep PT distribution at the LHC. So with that, one can already compare, and this is done on the right, to the charged pions, which are in red, and the d mesons are in black, in order to ask the question whether there is a difference, which is what would be expected from color charge dependence or mass dependence of energy loss. And here, yes, there is a difference around 5 to 10 GeV. However, there are also several confounding factors, so to speak, if you look at data from this point of view, like the role of flow and the role of hadronization, and there is no definite answer on the comparison between d mesons and pions, and also its origin of a possible difference. Now, we also have abundant measurements of beauty since run 2 of the LHC, essentially. And so here you see a nice summary by Jing Wang, the World Open Beauty data in central collisions on the left and centrality integrated on the right with ALICE, CMS, and also STAR data. But to make a bit more of a physics discussion, of course, we compare with charm, and this is a compilation by Roberta on the left with charm in red, and beauty or better beauty decay particles, d mesons, J psi electrons in blue. And in the region around 10 GeV, there is the data suggests that the beauty RAA is larger than that of charm, which is what is expected and may be related to larger energy loss for C than B quarks. And in this double ratio on the right, there is a ratio of non-prompt to prompt d mesons from ALICE compared with models. And we see here this increase with respect to 1 at around 5 to 10 GeV is seen also in the models where it comes from larger energy loss of charm with respect to beauty. And for radiative energy loss, this is the famous, let me say, dead cone for gluon radiation that we are after since now a couple of decades. And meanwhile, ALICE has seen it in PP collisions using detagged jets and a sophisticated declustering analysis that builds essentially the Lund plane, mapping the splittings in KT and angle. You see for D mesons and for inclusive jets. And if you select a region and you make a ratio of D over inclusive, then you see a suppression in D jets that corresponds to radiation at small angle with respect to the radiator, which is a proxy for the charm quark while it evolves in the jet Parton shower. So this is the first time that the dead cone is seen directly in PP collisions. Now moving on with the time of the collision, of course, one asks whether by interacting or interacting several times, the charm quarks that have lost energy come to thermalization with the system, and also what happens for beauty quarks. Now, this is another summary plot by Roberta where charm is in red. Also from, so this is only LHC, ALICE and CMS, and beauty decay leptons, electrons and muons are in blue. So there we see that at low PT, it seems that the charm V2 is larger than the beauty V2, and both of them are larger than 0. Of course, there are caveats. The uncertainties are significant, and one has to take into account that the decay kinematics in the case of beauty essentially shift any shape in PT. Now here it is a bit alleviated by the fact that these V2s in blue are quite flat with PT, so that effect may not be too large. So this difference suggests that due to the larger mass and therefore expected longer relaxation time, beauty may be farther from thermalization than charm. And at IPT instead we see that the values become similar, again with incisable uncertainties, and this is what one expects if the effect would only be a positive V2 from the path length dependence of energy loss, at least to first order. Now, to address a bit more the question whether charm reaches close to thermalization, in this figure we can compare the open charm here in orange, prompt D, with the J psi, so CC bar states, and also with the pions that are shown in white. And we see at intermediate PT, let's say of the order of 3-4 GeV, a hierarchy. So the pions have more V2 than the D mesons, and the D mesons have more V2 than the J psi. So here, this is consistent with the scenario in which the charm quarks have a V2, and there is then V2 propagated, let's say, to the D mesons via the mechanism of hadron formation by recombination. For the upsilon instead, which are the blue points here, we see that there is no indication for positive V2, and it is instead smaller than that of the electrons from B decays. This is, however, not suggesting, or let's say not conclusively telling us that B quarks don't flow, so to speak, because due to the large mass of the upsilon, a possible flow would be visible at even higher PT than what is probed here. So the new direction in the sector of heavy flavor flow from the experimental point of view are twofold. On the one hand, the higher harmonics, and here we see a nice measurement of V3 of the mesons. This is shown in blue, and we see that like for V2, also the V3 of the mesons is lower than the V3 of charged particles. This is shown as a function of centrality. And on the other hand, the studies that try to correlate directly the V2 of charm quarks with that of the bulk. This is done by Alice with event shape engineering. And what is seen is that if you select for a given collision centrality class events with small bulk flow, these are the blue points here. Also the D meson flow, or V2, is lower than in unbiased events, and vice versa. If you select events with high bulk flow, also the D meson V2 is higher. So there is a correlation between the V2 of D mesons and that of the bulk. Now, moving to the last stage of the collision, hadronization. Of course, it is very relevant to ask the question, what are the hadronization mechanisms of charm quarks? And we have seen that there are indications of recombination from several observations, and if one looks at a variety of charm mesons, one would expect an increase of the baryon to meson ratio in case of recombination, and also considering that the system is rich in strangeness, an increase of the strange to non-strange ratio. So starting from this one, this has been studied with D sub S at RIC and at LHC, and it has also been studied with the B sub S in the B sector at the LHC, as you see on the right. So for D sub S over D0, essentially the results are similar between RIC and LHC. There is also no evident centrality dependence, and there is only a weak hint of an increase with respect to proton-proton measurements. And at RIC, the conclusion is also limited by the fact that there is no measurement in PP collisions yet. So one has to compare with the event generators. And for the D sub S, the uncertainties are large, but also here there is a hint that the RAA of the B sub S is or may be larger than that of B plus mesons in this case, here around 10 GeV. But of course also here future running will have to address these questions. In the sector of comparing instead baryons to mesons, this is done with the lambda C over D, and here there is a compilation of measurements in PP and AA collisions, and for AA there is LHC and also RIC with the measurements by star. There is also a line that indicates the baseline from a plus a minus, and I already said that in PP already in red we see an increase with respect to plus a minus. Now looking at AA, the situation is not yet clear. So measurements are consistent, first of all, between experiments and also between RIC and LHC. And one may see some hint that it may be larger than in PP, but this is still not conclusive within the uncertainties. And at RIC, there is no measured PP reference, which again limits a bit the conclusions. Now, one word to say that, so at the beginning, I showed the effect in PP collisions. Now, that was also studied by Alice as a function of multiplicity. And so in PP, there is a lot of life. So this lambda C over D increases with increasing multiplicity already in PP, as you see here on the left. And on the right, there is a plot, so a lambda C over D strangeness enhancement, so to speak, plot. Sorry, baryon enhancement, so to speak, plot as a function of multiplicity. And of course, it recalls the so-called strangeness enhancement plots for hyperons. Now here, one sees that by comparing low multiplicity PP and then lead and high multiplicity PP, there seems to be an increase. This seems to be already quite clear. What is not clear is whether between high multiplicity and lead there is a change. That is an open question. And of course, very interesting would be also to extend to lower multiplicity to see whether you connect back to the small value 0.1 that is seen in E plus E minus data. So this is another plot that will benefit a lot from future experiments and running. And by the way, so this question of hadronization is not only interesting per se, but it has also deep implications on studying the QGP. For example, extracting the heavy quark transport parameters. This is the diffusion coefficient, D sub S, as a function of temperature. And I show an interesting exercise that was done by Salvo from the Catania group for the HL-LHC report. So, okay, left is run 1 and 2 data, but let's focus on the plot on the right. This is with the pseudo data from LHC run 3 and run 4. And the size of these blue and red bands reflects the expected precision of the data. And the blue is in the case in which you don't consider coalescence or recombination of charm, only fragmentation. And the red, coalescence plus fragmentation. So one sees that the way in which hadronization occurs and is described in the model also affects quite strongly the value that you extract from the diffusion coefficient. So it is crucial to pin it down. Now, briefly in the last few minutes on the experimental outlook. So I have repeatedly tried to raise interest on future data. So where are we going? In particular, in the heavy flavor sector. There are two main frontiers to enhance the physics reach. One is increasing the rate capabilities and acceptance. So number of heavy flavor particles that you can potentially measurement. And the other is increasing the tracking precision. So better separation of heavy flavor particles from the backgrounds. And okay, I will not repeat. This is crucial essentially for all the measurements that we want to do. And in this graph, one sees a bit where we are going in this two-dimensional improvement map. On the vertical scale, the precision of the tracking, so low is better. And on the horizontal scale, the acceptance times interaction rate, so to the left, of course, is better. And there you see the path of Alice between run 2 and run 3-4, which is now at our doorstep, and maybe a little bit more increase of precision in run 4, and then much more higher rate with the RAN5 plans that I will mention later. You also see star and then as Phoenix, so the situation at RIC, and on the higher side, the path instead of Atlas and CMS with an increase in the rate between run 2 and run 3 for minimum bias events, and then in run 4 also a large increase in precision. So I don't have time to go in detail through the next slides, but just let me say a couple of things for each facility. So
you have 2 minutes, Andrea.
Okay, yeah, thank you. So I also want to mention the SPS. The SPS in the near future, or in the second part of the next of this decade, let's say, could also become a source of precise charm measurements, in particular from the upgrade of NX61 and with much more precision from the newly proposed NA60 plus. At RIC, of course, as Phoenix will be the ultimate performance experiments on the one hand for jets, but for what is of interest today, for heavy quarks, of course. And I don't have to inform you too much on this. Alice for run 3 is going to have a better tracking precision by a factor 3, 50 times faster readout, so much larger samples. And for run 4 is preparing a further tracker upgrade, this fully cylindrical inner barrel that you see sketched here in the corner, that will improve a lot for the short-lived charm baryons in particular. And also at the LHCb, already from the run 3, we'll have better performance in LED. So we should see results down to centrality of 30% from LHCb, and they have a new storage cell for a much enhanced fixed target program. And Atlas and CMS with the phase 2 upgrades in run 4 will add new trackers and particle identification, which of course will help for HF measurements. So here you can see some snapshot of the expected performance, but I will not describe it in detail. Here you see for the baryons at S-Phoenix and Alice, the lambda B, and then for CMS, the B and the B sub S that I have shown earlier. And before closing, a sketch of the detector that is being designed, concepted by essentially the Alice collaboration. So in short, one could say a silicon-only heavy ion experiment for the LHC run 5, a fast ultra-thin detector with precise tracking and timing. This is, of course, one of the main goals is to have ultimate performance for not only for HF, but also multi-HF states, in particular multi-charm baryons. So to conclude, I look forward to heavy flavor transport properties extracted from the data that I have shown, and also, of course, setting the stage to extract this then systematically with the new data that we get. And I wish you an interesting and productive workshop.
Okay, thank you very much, Andrea, for bringing us up to speed with this presentation. We still have time for a few questions right now, but of course, we will come back to many of the things over the course of the week. So who would like to ask a question? Please raise your hands. Nobody yet?
May I ask one question?
Yeah, sure, go ahead.
I have a question about lambda C enhancement. You showed the enhancement as a function of transverse momentum. Have you counted only number and compare with the statistical model? I mean, I'm not. I don't want the ratio as a function of PT, but just number, produced number of lambda C and D, and how much is it different from a statistical model?
Yes, so I don't have a plot here. So this was compared. Well, I don't have a plot. It is larger than in the statistical model, but now quantitatively, I don't have the number. Maybe
it depends a bit on the extrapolation, because you see that the measurement only starts at 2 GeV, but it's about a factor 2 higher in experimental data. So I see a question by Xinyang.
Yeah. So I have two. I have two questions regarding your early slides. One is about the electromagnetic effect, and you compared. There's two data sets, one from STAR, one from I think Alice. The V1, yeah. And I think your statement is that the STAR data is consistent with the slope is 0. Well, if you look at the upper plot, it is I mean, I don't think you can say it is 0, the slope, right?
Yes, I meant on the delta V1.
Yeah. Oh, the data V1, the data V1.
Yes, I meant on the lower plot, the delta V1, which is expected.
The theory calculation is small, but definitely is not 0, right? The theory calculation.
Exactly. Yes.
Yeah, but this slope is the theory, at least the theory calculation slope is the sign is different than the Alice result. Any explanation?
No, actually, no. So there is essentially no calculation to which the Alice results can be compared directly. And if one takes the calculations for Rick, indeed the sign is different. So the value is, of course, much different.
Yeah. The sign is also different.
But the sign is also different, which could be due. So you see, there are these two effects: the effect induced by the magnetic field directly, and the effect induced by the corresponding electric field. And it could be that between Rick and LHC energies, the net effect of these two has a different sign.
I see. The second point is
make it quick because we're already running late.
I don't know whether you have look at the you talk about the V2 from PLED for D mesons.
Yeah, no, that I didn't include. No.
Yes, so that's another point. I think it's pretty big from what I remember, and
yes.
And then there is no modification of D meson at high PT, but V2 is still big.
Yes, indeed. I was actually alluding to that when I was asking this question, whether one can use D mesons from minimum bias PLED to constrain nuclear PDFs.
Yeah.
Having that in high multiplicity PLED, we see azimuthal anisotropy.
Okay, thank you. Yeah.
Okay, so if it's quick, we can still take Vincenzo.
Mine was just a quick comment on the question of Xinyan about the delta V1 at LHC. Essentially, we have published the paper in which we see that to get such a large delta V1, you need a magnetic field that goes down very slowly, like 1/T. while usually, I mean, this is just the slowest one when you study the chiral magnetic effect. In that case, you produce by Faraday effect, a small electric field, and then you can get such a large delta B1. But of course, it's difficult to get from the solution of the Maxwell equation that such a slow decaying field.
Yeah. Thank you for this comment. Thank you. And so I think we really have to move on now. Thanks again, Andrea, for this very nice overview. And now we come to the theory side and to Peter Petretsky. Peter, can you start to share your screen?
Sure. Let me start sharing. Screen.
Okay.
Let me go to the slideshow. Okay, thank you very much. Do you see my screen?
Yes, it's fine.
Okay, good. So I'm going to talk about a heavy flavor probe and lattice QCD. And I organized my talk around 3 different bullets plus a summary. So first I will just give a brief introduction to the confinement properties of and quark-gluon plasma. So that will be lattice QCD versus weak coupling. Then I will talk about charge correlation and fluctuation, and possibly relation to charm hadrons about EC. And the bulk of my talk will be about lattice determination of the heavy quark diffusion. I will introduce the electric field correlator method. I will review results from quench QCD. We'll discuss some new results on 1/m effects in Langevin dynamics, and as well as a method of gradient flow to do this calculation. And finally, I will give a summary. So of course, we know what the transition temperature in QCD, or the crossover temperature, and it's related to chiral transition. It's known by now by 1% accuracy. On the other hand, we don't discuss so much about the deconfinement temperature in QCD because it's not so obvious how to define deconfinement. We know how to define deconfinement in terms of color screening, where we have an order parameter in SUN gauge theory, so no dynamical quarks. And then we have the order parameter, which is the particle loop, or if you renormalize it, we get the renormalized particle, which is exponentiated free energy of the isolated static quark. Now, in this figure, I show the renormalized particle loop as functions of temperature in pure glue series. So those are the blue and red symbols. Then in full QCD, the green and the black symbols using 2 different approaches from different groups. And we see that at high temperature, the behavior of the particle loop is quite similar, but at low temperatures, there is difference. In fact, at the chiral transition temperature, we don't see much going on in the renormalized particle loop. However, if you look more closely, so we, instead of looking at the particle loop itself, we look at the derivative of the free energy of a static quark, which with respect to temperature, which is the entropy. Then we see a big peak in the entropy of a static quark at a temperature which is coincides with the chiral transition temperature. So the onset of color screening in full QCD seems manifesting in the peak of the entropy of a static quark. Accidentally seems to coincide with the position of the chiral transition temperature. So in that sense, we may say that the chiral transition temperature and deconfinement temperature agree. Now, the other way to look at deconfinement, and that actually, sorry, jumped too fast, look at the Taylor expansion of the pressure in terms of the chemical potential of the relevant quantum number, like a baryon chemical potential, electric charge, strangeness, and charm chemical potential, or equivalently in terms of the chemical potential associated with U quark, D quark, S quark, and charm quarks, for example. And all these Taylor expansion coefficients are evaluated at zero chemical potential, which is straightforward to do in lattice calculation. Now, these Taylor expansion coefficients then give us a fluctuation of conserved charges, or the correlation between different conserved charges. So in particular, the second order fluctuation is, or Taylor expansion coefficient, just the usual fluctuation of some conserved charge X, whereas the off diagonal correlations are given by mixed derivatives. So for example, taking derivative with respect to chemical potential X and Y, we have the correlation between conserved charges X and Y. And these quantities then carry some information about the carriers of conserved charges, whether they are hadrons or quarks. And in that sense, we could probe deconfinement by studying correlation and fluctuation of conserved charges. So let me just show how the lattice results on quark number fluctuations. In that case, I'm talking about the light quarks, so U quark number fluctuation compared with a weak coupling. So I show really the high temperature result about 300 MeV. And I normalized everything by the ideal gas values. And one sees that in principle, at high temperatures, the weak coupling results are relatively close to the lattice results. And furthermore, we also considered the correlation between two conserved quark number U and D. And these correlations are pretty small. In fact, if you would have a non-interacting quark gas, this calculation would be exactly zero. Of course, if you have interactions, they appear at some high order in the weak coupling expansion, and the weak coupling result is shown as a red band in this case. And we see that again, up about 300 MeV, we see an agreement with this weak coupling calculation for this correlation and between U and D quarks. So now that was a large degrees of freedom, so we could look at the similar results for the charm. So we could consider charm fluctuations and charm correlation with other quantum number, like the baryon numbers. And here I show different quantities, in particular the ratio of baryon charm correlation at different orders. So fourth order and as second order versus fourth order. And this ratio constructed such that in hadron gas, they should be exactly 1. And that's because it doesn't matter which particular correlation you take into account. You have baryons, the baryon number carried by only by baryons. So you have B equal 1 contributing only. And because the charm quark is also heavy, effectively only C equal 1 sector contributes. So about below the transition temperature, all this ratio should be equal to 1. But if you go to very high temperatures and certain ratios where you take more derivatives with respect to baryon number will be different, because now you may have a fractional carriers of a fractional baryon numbers like 1/3. And in fact, you see this transition where you go from a hadronic picture where all these ratios are 1 to non-interacting quark gas picture where you have charm quarks which also carried 1/3 of a baryon number, and this is this dashed line on the top of the figure. And of course, you don't quite reach that limit, but you're getting close within 10%. And then of course the question, what happens in between the region where you are, so to say, above the transition temperature, but not quite in the regime where this correlation are close to the non-interacting quark gas. Of course, we could make a comparison of this correlation between baryon charm number with the hadron resonance gas model. And of course, when we do this comparison using only the hadrons which are known in the particle data group, then we get a quite big difference compared to the lattice. But once we include not yet discovered states, then actually the agreement between the lattice and hadron gas works very well. Now, we could look at this further, maybe at the high temperature, and look at the charm fluctuation in particular. And in principle, these are useful if you're interested in kind of quantifying the properties of charm degrees of freedom. So if you assume the charm degrees of freedom about 200 MeV or so are charm quarks, then of course they need to have some thermal mass. You apply a quasi-particle picture, and in principle you could fit the lattice data shown in the left figure with a simple massive quasi-particle model and determine the temperature-dependent charm quark mass. And what you see is that there is a significant temperature dependence. So the charm quark mass defined as a quasi-particle mass to describe the charm fluctuations actually changes from 1.8 GeV to something like 1.4 GeV at the highest temperature. Now, of course, we could also look at correlation between charm quarks and light quarks. And here I show these correlations for kind of two type of correlations, even, so 2-2, and even odd, which is, we know from weak coupling should be very small. And both, of course, have been calculated in the weak coupling results. And we see that at very high temperature, the correlation between U quark and charm quark is very small, and in fact compatible with weak coupling results. But below 200 MeV, you have a very large deviation from the weak coupling results, so this correlation become pretty large. And then the question is, if you have such large correlation between U quark and charm quark, how do you explain it? So one possibility is to assume that at some temperature region below 200 MeV and the transition temperature, you have several charm quasi-particles. So you have the charm quark as you would expect in the deconfined medium, but you also allow for charm baryons and charm mesons. And if you have for 3 different quantities, which we taken to be the charm fluctuation and the 2 baryon charm correlations, so 1-3 and 2-2, then you can extract 3 partial pressures. So you write the total charm pressure as sum of the charm quark pressure, charm baryon pressure, and charm meson pressure. And then using the lattice data, you could extract the 3 partial pressures. And here I show the results now normalized to by the charm pressure to have it in a reasonable scale. And what you see is that if you look at the charm pressure at very high temperature, not very high, but let's say about 200 MeV, it gets close to 1. So the entire charm pressure is actually dominated by quark degrees of freedom. But at lower temperature, that's not necessarily the case. You have also significant contribution from charm meson pressure in blue and charm baryon pressure shown as red symbols. And the idea is that charm hadrons, they don't, there are some in medium charm hadrons which still may exist above the transition temperature, and they give some additional contribution to the charm pressure in form of baryons, some in medium baryon-like and meson-like resonances. Okay, so now let me go to the discussion of the lattice determination of the heavy quark diffusion constant. So in Langevin dynamics, we have 2 low energy parameters. That's typically eta, the drag coefficient, and kappa, the heavy quark diffusion coefficient. And of course, we know in thermal equilibrium they're related. And in lattice calculation, we would like to determine one of them. And because lattice calculation is thermal equilibrium, of course, the other then follows using the standard relation of dissipation fluctuation theorem. So the way we proceed, we consider the correlation function of charm currents. So we consider the charm current correlator in real time and make the Fourier transform, which gives us a spectral function of the corresponding current correlator. And if you look at the spatial components of the current correlator summed over the spatial indices, and at very small frequencies below some cutoff frequency, which I denote omega UV, there is this the spectral function has a Lorentzian form with a parameter eta, which is nothing but the drag coefficient. So in other words, the drag coefficient appears as a width of this Lorentzian at very small frequency, so the width of the transport peak. Sorry. And of course, then you can use the relation, the standard fluctuation dissipation relation to relate eta to the spatial diffusion coefficient, which in some sense is a mean free path of the of the light degrees of freedom in quark-gluon plasma in the weak coupling results, or the heavy quark momentum diffusion coefficient kappa. Now note that you really need to determine the width. So because the area under the P, this transport peak is fixed to be the quark number susceptibility times the velocity squared, which is T over M in the heavy quark of the heavy quark. So of course, here I'm working at the leading order T over M, and I will discuss corrections, what happens at next to leading order. So the problem is that if you have a large quark mass, so you're discussing the heavy quarks, and this peak is very narrow, and determining this very narrow transport peak is a real challenge for lattice QCD, and I would say that's extremely difficult task. So there is an alternative approach to circumvent this problem, is actually to use the heavy quark mass as a tool. So in the heavy quark limit, you could define the momentum diffusion coefficient kappa, not in terms of the current correlator, but in terms of the time derivative of the heavy quark current correlator. So you just, instead of looking at correlator ji, you look at the corresponding derivative. And if you use now the heavy quark expansion, so it takes the limit m to infinity, you could relate this current to the electric field, sandwich between the two heavy quark fields, which are Pauli spinors. So because they're heavy, you could integrate out the heavy quark field phi and theta. And in that case, your correlation function reduces to the correlation function of two chromoelectric fields. So that is a chromoelectric correlator GE. Once you have it, this correlation function, you could also rewrite in Euclidean time in tau, and this Euclidean correlator then has a spectral representation in terms of spectral function rho omega, rho E omega. So E is for the electric. And in this case, the transport coefficient is given by the low frequency limit of this spectral function divided by omega, but there is no transport peak here. You just have a smooth approach to the zero frequency limit. And that is demonstrated in this figure. So at high frequency, the spectral function behaves like omega cubed. But as you go to lower frequency of order the temperatures, this behavior changes, and eventually it's supposed to go to a constant behavior. And actually at very high temperature, you could get this constant behavior from next to leading order calculation of the spectral function. And the intercept of this line actually gives you the heavy quark diffusion coefficient at a leading order. Now, since you have this lattice correlation function and the spectral function has a relatively simple form, so it's appears to be a viable approach to extract the heavy quark diffusion from the lattice. But there is a challenge, and the challenge is noise in the Monte Carlo simulation, and you have to deal with this problem. And to deal with this problem in pure gauge theory, multi-level algorithms plus link integration have been proposed. So the multi-level algorithm is the key. It was proposed by Usher Weiss. And here I show the noise reduction with standard algorithm, which is blue. You see huge fluctuations. Once you put the multi-level algorithm, those are the yellow diamonds, you see much reduced fluctuation. And of course, if you put on top the link integrations, and it's further, the fluctuation are further reduced. So with this technique, it's possible to reduce the noise and get small results for the electric correlation function. In addition, you have to multiply it by the renormalization constant, which is also known, at least at one loop level. And finally, in order to show the lattice results on a reasonable scale, you normalize by the leading order result just to avoid very large vertical scale. And you see that on this figure shown on the right, that the lattice results on different lattice spacing actually very precise. So it is possible to determine, at least in pure gauge theory, to determine the correlation function very precisely using this technique. Now, once you have the correlation function, you still need to extract the coefficient. So you have to have a model for the spectral function. And as the simplest model, because the spectral function is simple expected shape where you have an intercept at very small frequency, which gives you the kappa, the heavy quark diffusion coefficient, and it should be essentially the vacuum spectral function going omega cubed. At high frequency, you just interpolate between those two extreme regimes. So you have several possibility how you do the interpolation between those two regimes, and that of course it gives you different estimate for the final kappa. So what you do, you take the low frequency part, which just kappa omega, kind of glue together with the high frequency part with some intermediate behavior, and depending how you model the intermediate part, you have some scattering of a kappa. And here I show the results from Bielefeld. And you see that depending on how you model the spectral function, you get some scattering between 1.8 and 3.4 in units of t cubed. Now, similar calculations have been done recently, again using multi-level algorithm, but now in a wider temperature range and using slightly different way to model the spectral function, but using more or less the same idea. And here I show the result. There will be a dedicated talk by William Milano on this result. And again, you see the lattice determination for several temperatures in black error bars, and then compared with the V-coupling results shown as an orange band. And you could also fit the lattice results by some leading order inspired ansatz with some parameter to fit the temperature dependence. And you see that the temperature dependence of kappa seems to agree well qualitatively with the next leading order result, but also there is in principle within errors, it seems to be compatible with the next leading order result. Then in the bottom figure, I put together all the results. So that's previous results from Bielefeld shown in this orange triangle, previous order calculation by Banerjee, Data, and Gawai as a blue, and finally the new results in the black one. And in principle, they all agree quite well. There is one set of lattice calculation from Ding et al. From 2012, which uses correlation function, direct charm correlation function, and try to determine the eta, so the drag coefficient from the transport peak, and those the corresponding d spatial diffusion constant, which you could essentially also relate to kappa, seems to be much smaller than the other determination, and I would argue that's because the width of the transport peak is really difficult to determine for the heavy quark mass. So that's why you have these results having a much smaller d, or conversely much larger kappa than the other results. Now, there have been new developments basically this, last year, and that's one is how to calculate the next leading effects in 1/m expansions, or in the one of the inverse heavy quark mass. And for that, you have to realize that if you consider kind of a microscopic dynamics behind the Langevin, then of course the electric correlator is a leading order in 1/m, so you only assume that heavy quark, on the heavy quark only electric fields act. But if in the next leading order, in 1/n expansion, of course, there is also magnetic fields contribute to the chromo-Lorentz force, so to say. So the force correlator will be then given by electric correlator, and then magnetic correlator times v squared, which in the thermal medium is T over M, so it's 1 over suppressed. Then in Langevin dynamics, there is a relation, of course, in the equilibrium. So the P squared is 3 kappa over 2 eta. And of course, now if you go beyond the leading order in 1 over M, you also have to think what is P. So you have to use a relativistic definition, it turns out, if you want to avoid some trivial 1 over M correction. And furthermore, you also have to think what is the quark mass. So I discussed that there is certainly the in-medium quark mass. In this case, you have to think about in-medium kinetic quark mass. And then with all that, there is a modified relation between the drag coefficient kappa at order, which goes like 1 over M again. In turn, you now need to consider the magnetic correlation function. So say the correlation function from a magnetic field, which has also a similar spectral representation to the electric one. And it also has a low energy limit. It's give you some effective diffusion constant. So the diffusion constant that goes into Langevin dynamics actually is kappa E, which we extracted previously from the electric correlator, and 2/3 v squared kappa B. So that represents the 1 over M suppression effect. So in principle, you could also calculate the chromomagnetic component to it, and then you have a correction to your kappa just from the fact that you have a heavy quark mass. There is a technical challenge in this calculation that unlike the electric correlator, the spectral function of the chromomagnetic correlator has non-trivial anomalous dimensions. So there is a scale dependence, and that of course will complicate the kappa beta extraction. On the perturbative size, of course, kappa B cannot be calculated on lattice because it's chromomagnetic, so it's sensitive to the non-perturbative magnetic mass already at leading order. So here you really need lattice to get any estimate for this number. Then another technical kind of development, which is extremely important, is a gradient flow. So the gradient flow is essentially the replacement of the original gauge fields by what is known as flow gauge fields B, was proposed by Lucier. And the B fields satisfy essentially a gradient flow equation, which has a form of diffusion equation. Because it has a form of diffusion equation, as you evolve the gauge fields B in this fictitious flow time, essentially the original gauge field, which gives the initial condition for these flown gauge fields, gets smeared in the radius proportional to square root of 8 times the square root of the flow time. And because of this smearing of the gauge fields, you filter out the ultraviolet component of the fields, and you achieve a noise reduction in the electric correlation function. And of course, the noise reduction is very significant. And here I show the same quantity, the electric correlator normalized by the corresponding leading order result, just to bring out the scale. And you see that the error bars in this calculation, depending on the flow time, are very small. So it's very small, at a small flow time, if you would go close to 0 flow time, of course, the error bars will be humongous, so it won't fit in the plot. But if you go to not very large, but some amount of the flow time, the error reduced, and the larger the flow time is, the smaller the error get. Of course, to recover the physical result, you have to take the flow time 0 limit, but you only can take this flow time 0 limit if you take first the lattice spacing goal 0 limit. So first, the proper order of the limits is that you take the continuum limits equal to 0 first, and then you can take the flow time limit. And in order to do this extrapolation in a meaningful way, you need very large n tau. So in this calculation by the Bielefeld group, they use n tau up to 32. So once you do all that, and you now calculate the Euclidean correlation function normalized by the leading order result, here I show the gradient flow result and the multi-level result in yellow. So that's the previous results from where I got the diffusion coefficient. And you see that they almost agree. There is some systematic shift between the two, and that's most likely due to the fact that in the gradient flow result we use perturbative calculation of the renormalization constant, whereas gradient flow is a non-perturbative renormalization. Most importantly, the nice thing about this method is that it could be used in full QCD, so the QCD with dynamical quarks, and therefore now we're in position in principle to consider calculation of the heavy quark diffusion constant also in QCD with dynamical quarks. Okay, so that brings me to my conclusion. So I discussed that the chiral symmetry restoration and deconfinement appear to happen at the same temperature, and deconfinement can be characterized in terms of color screening. At high temperature, let's say about 300 MeV, quench QCD, so pure goose theory and full QCD are pretty similar in terms of color screening. So at least quench QCD can be used at high enough temperature as qualitative guidance. We calculated the heavy quark diffusion coefficient in quench QCD, and at present it's the best known transport coefficient from lattice. And the value in terms of the spatial diffusion coefficient D, 2 pi D is between 1.8 and 3.4. The lattice results on the heavy quark diffusion coefficients are comparable to the NLO results within errors. Now we have a means to calculate the 1/m corrections on the lattice. We also see that the gradient flow is an efficient method to reduce the noise, and that will enable to calculate eventually the heavy quark diffusion coefficient in full QCD. And finally, the physics below 200 MeV, but kind of about TC is strongly interacting. And then one interesting question is whether charm hadrons can exist there. And in this region, of course, we have no knowledge about the transport properties. So thank you very much.
Okay, thank you very much, Peter, for this nice progress in lattice QCD. Let's see, we already have one question by Xiaoyun Yao. Please go ahead.
Hi, Peter. Thank you for the nice talk. Can I ask you a question about the anomalous dimension for the BB correlator? Like, there are intuitive understanding why in the EE correlator, the anomalous dimension is 0, but for the BB correlator, it's not vanishing?
Well, I mean, it comes out essentially at next to leading order. I mean, the argument, I would say, my naive understanding at least, that of course, the starting point of all this discussion is vector current correlator. So the vector current is conserved, and therefore there is no anomalous dimension, in a sense that if you formulate the vector current on the lattice, of course could be a finite renormalization, because what conserved on the continuum won't be conserved on the lattice. So, but of course, as you go closer to continuum, eventually should recover the conserved current, so there could be no scale dependence. And the electric correlator, if you do a 1/m expansion, is a leading term to the electric current, and therefore it also doesn't pick up the anomalous dimension. But what you mean by 1/m correction, of course, somehow is somewhat arbitrary, right? Because 1/m in particular, so what is m? Right? That's you think it's a pole mass, but the pole mass is not very well defined because of the confining nature of QCD. So that's already kind of a bit problematic, and I guess that's why the magnetic correlator could pick up an anomalous dimension. And that the way you see it is that the high energy component, the high frequency component of the spectral function has an explicit scale dependence, which we have to deal with that.
I see. Thank you.
Okay, next question is Anton.
Thank you, Peter, for this very nice overview. Early on, you showed this comparison of the lattice susceptibilities with the extra states in the hadron resonance gas model.
Mm-hmm.
And the question is, should actually the hadron resonance model describe the lattice up to 180 or even 170? Shouldn't it maybe be?
Yeah, I mean, it should not. I mean, it doesn't necessarily. It's. I mean, it's a kind of unfortunate that I mean, the lowest temperature we have is like 155, so it's just at the borderline where it makes even sense. But you see that the effect is very big. So in order to argue for additional states, you probably ideally would need to add some calculation to the lower temperature. But my feeling is that, of course, I mean, eventually it won't work and it will break down, but it will depend on which order in fluctuation. If you go to second order fluctuation, for example, the experience is that it doesn't break down immediately at TC. It's actually, well, it's at least qualitatively, it's in the similar ballpark. And if you have kind of, you are missing a large part, let's say at 155 and maybe 160, maybe you will be missing something also at lower temperature. So that because the curves are smooth. Now, if you go to very high order fluctuations, there are some other effects, which probably for charm is not so relevant because the charm density is very small, the density of charm hadron. So this repulsive interaction between charm probably won't play a role. So therefore, I would expect that it gives you some guidance that maybe you're probably missing something, but in order to really make the case, we need to extend the calculation to over time.
Guidance, I think, is the right word, and not a demonstration at this point, right? I think that's yeah. Thank you.
Okay, then we can still take the question by Jörg Eicheding.
Just a question concerning the CC bar correlations, because you showed they contribute quite a bit to the pressure, even at high temperatures. The question is, can one say anything about the binding energy of the CC bar pairs, whether these are really bound state or whether these are basically resonances?
Well, I mean, it's definitely if you are there, it's some broad resonances. So it's actually not CC bar; it's like CU or CS or whatever. So charm light, so it's heavy light states. Yeah, I mean, they have to be broad because otherwise, how you would explain that their pressure goes to zero, right? So there are probably some broad structures, resonance structures to start with, and their width then increases with the temperature to the extent that you can't recognize them and they don't contribute to the pressure.
Yeah, but is there a limit in the width when they contribute still to pressure? Because at the end of the day, these are up in a seek walk.
Yeah, well, I mean, of course, when you have a stable or very narrow quasi-particle, well-defined quasi-particle, the spectral function is a delta function. If you have thermal damping of whatever degrees of freedom you have, whether it's kind of hadronic-like or quark-like, it will have a thermal width. And the thermal width, of course, is significant. And once you have a thermal width, then typically what you find that the contribution is smaller. So you could essentially annihilate certain states to pressure by making them broad.
Okay, thanks.
But I mean, as you said on your last slide, what you see from the pressure is that the system is strongly interacting, and then in principle, a quasi-particle picture doesn't make sense. I mean, the pressure, if you just do it in the UTS sector, it is.
Yeah, I mean, so certainly for light, it does not make sense. And then the question is how you, so for light, of course, I would say I can make no statement. Then the question is, what do you say about heavy? I mean, typically we say about the heavy degrees of freedom, charm or bottom, they are kind of charm quarks. But then of course, in principle, all these correlations should not be there, right? If you have charm quarks only. And then the question is, if they're not charm quarks because they correlate with U quarks, what are they? And in principle, yeah, I mean, I don't know. So certainly you may say that this quasi-particle picture is too naive, but I don't know anything better. So certainly, let's say it's maybe a step less naive than just assuming that you have only charm quarks and all the charm degrees of freedom are carried by quarks, because you have this correlation you have to model somehow, right? And in Langevin dynamics, you don't have this effect there. So you have to think a bit.
Yeah, I'm sure we come back to these questions in the course of the week.